organizers for giving me this opportunity to tell you something about this work done in collaboration with Seifert, Bonetti, and Jinxian. And yes, I will try to start with some sort of broad introduction related to the main themes that appear in the title. And I would like to start with a more physicsy angle. This is my background is more physics. And I think we can all agree that one of the more important problems in various areas of physics, actually, ranging from condensed matter to high energy theory, but also quantum computing, is try to characterize in a precise way possible infrared phases of quantum systems that we might be interested in studying. This is a very hard problem in general, and what has been observed in the past is that symmetries usually provide us with a very powerful tool to try to tackle this problem, and in many cases get satisfactory answers. And for instance, one of the most famous ideas is related to spontaneous symmetry breaking as a way of characterizing phases, which is embodied in the Landau paradigm for ordinary group-like symmetries that has an enormous success. On the other hand, we do know that the Landau paradigm for ordinary group-like symmetries is not quite the end of the story, as there exist non-trivial phases of quantum systems that elude the traditional Landau paradigm. And the more sort of prominent examples of those are found in 2+1 space-time dimensions and are usually referred to as topological orders. And we do know that they are not a trivial phase because they exhibit some non-trivial properties. For instance, they have robust ground state degeneracies. And another possible diagnostic tool is entanglement that these systems exhibit. And therefore, we know that there is very interesting physics out there that seems to go beyond the traditional paradigm. And incidentally, these systems also have experimental realizations, for instance, in the fractional quantum Hall effect. So there is a great motivation physically to study sort of orders that fall beyond the usual pattern. And I would say that for the purposes of this talk today, a more useful way to think about the properties of these non-trivial or topological orders is to focus on their line operators. So these are phases where we don't have any non-trivial local operator, but we do have non-trivial line operators. Those are the word lines of the anyons of our system. And their word lines indeed can have non-trivial braiding, non-trivial twist. They can fuse in interesting ways. And all these essentially can be put together coherently in the framework of a topological QFT. Mathematically, this is one of the situations where actually there is a very precise mathematical language to describe the physics given by modular tensor categories. And as many people in the audience know extremely well, it has, on the one hand, it's extremely rich mathematically, and there is a great motivation to study it in pure math. And in terms of relations to other areas of physics, historically, there's a strong connection with 2D CFTs, but this also extends to the study of quantum groups or in the world of topological quantum computations and more. Now, it is actually quite hard to get a precise idea of what the space or the world of the modular tensor categories is, as I will review a little bit in more detail later. The classification problem itself is actually very well posed and well defined, but nonetheless very hard. And therefore, if we want from a physics or a math perspective to try to learn more about MTCs, we have several strategies that we might follow. And here I'm just giving a few examples. For instance, something that is possible given the very sort of finite nature of the mathematical problem is a brute force scan. Essentially fixing the maximal number of anyons that we want to study in our system, we can try and go and really enumerate all the possible consistent MTCs, or say at least their modular data. And this has indeed been done. This is a tremendous effort, and up to rank 11 at the moment. So this gives us sort of a very hands-on way, but very expensive computationally, and maybe not necessarily transparent from more conceptual point. There are other ways. Zesting, for instance, is another way to sort of turn an MTC into another. So it's also a way of exploring the space of MTCs. And if we sort of switch gears and go towards something that's more physical in nature, there has been very interesting proposal and results in the literature aiming at trying to map MTCs from a physics perspective, using as an auxiliary tool, so to say, a suitable quantum field theory in 6D, a superconformal field theory. If this is reduced on suitable class of 3 manifolds, it is expected to give rise in favorable circumstances to these MTCs. So in particular, the setting that these authors have considered involves having a partial topological twist so that we preserve supersymmetry, and then argue by suitable arguments that we get a gapped phase in the IR, and nonetheless argue that it is non-trivial, and then indeed it has trivial anionic lines, and trying to understand their properties. Now, this approach is well understood, especially when we work with the rank 1 A series CFD upstairs, and we consider a class of 3 manifolds that are Seifert manifolds with 3 singular fibers. And this is already quite powerful. It gives us plenty of MTCs, but on the other hand, it's known that it's not going to be enough to go above rank 4. So when we were looking at this problem, at first we were thinking of possible ways of extending this paradigm. And this is super interesting, but in a sense, for us, it became something that we might want to do in the future. What we propose instead in this work is a slightly different approach. It was heavily inspired by the one I mentioned.
Already asked something for so you say it's not enough to reproduce the modular tensor for rank greater than 4, but why would you even expect that they all come from some? Is that something you would expect, or is it just a question whether?
No, it's more of a question. Like, the question would be indeed, if we were powerful enough to consider an arbitrary 6-dimensional starting point and arbitrarily complicated 3-manifold, could we hope to recover everything? It's a very open question. We set up to do something similar, but sure.
Probably maybe say that later, but so the anomaly of the modular tensor category, does that come in some easy way from the manifold? So that's the this e to the something central charge over 8.
Let's see, it is encoded, but I wouldn't say in a super straightforward. Indeed. So we were essentially, what we would like to propose is similar in spirit, but yet distinct in that we do not want to use the 6-dimensional viewpoint, and rather aim to constructing directly, so to say, a way of associating to some data consisting of a Seifert manifold and a complexified Lie group, a fusion category. And so essentially what I will be discussing is a proposal to define such a map. And we believe that it is interesting because we have checked in examples that it satisfies some non-trivial properties. And as a sort of appetizer, I can mention now that, for instance, the fact that we do get something modular at the end, it's not quite guaranteed in the process, but it's actually encoded in the topology of M3 and also in the choice of the Lie group G. So it depends in an interesting way on the input data, and we will see much more explicitly what I mean by this. Another important aspect of this correspondence is that one of the key ingredients that allows the two sides to be matched, as we will see later in greater detail, are flat connections on M3. So that essentially in the process of developing this map, we were also able to formulate some conjectures about the space of flat connections that I believe might be of more general interest, even beyond the specific problem at hand. And using this new association, Seifert manifolds and G to fusion categories, we were able to go beyond the rank 4 sort of barrier. And in particular, we are able to go all the way up to rank 5 and almost all models at rank 6, even though some are still eluding us. But we have some ideas.
The property of your three manifold being Seifert hybrid, is that an essential property, or is it just because this is the ones for which your particular tools apply?
So at the moment, our construction applies to Seifert manifolds only, but indeed, it's a natural question to ask if there's a way to extend it. So as of now, the Seifert structure is needed for us to run the procedure.
Just asking you if you expect that it's possible to continue for other three manifolds, or if you expect that it's only possible for.
I mean, from everything we know about the 3D correspondence for general three manifolds, what you get after, at least from the 6D perspective, what you get after compactification on, say, like a hyperbolic manifold is a CFT. That's not a topological, that's not a topological theory. Like it's a 3D n equals 2 CFT.
Absolutely.
I see. Okay, so this is a special feature of the manifold that makes it be.
No, that's a very good point. We know for sure that there is no reason to expect that the hyperbolic manifold would work. So let's have a first look at how this correspondence looks like. So there are going to be some symbols and some quantities in this slide that I haven't defined yet, but I've put this slide to give you sort of a first indication of the sort of map that we are aiming to construct and to study, and then we will have the chance to explore in greater detail the various parts of the proposal. So as I mentioned, on the one side, we have a geometry and the choice of group G, and the geometry is going to be a Seifert manifold, which is conveniently described in terms of some combinatorial data, some integers, p's and q's satisfying suitable properties. And the two sides of the input, the geometry and the G, talks to each other through this condition here on the first homology group of N3 with values in the center group G. So if we're given this input, we can get this output, and we will see precisely what these objects are. Let me emphasize some sort of coarse-grained feature of this construction. So first, in a sense, the geometry itself is made out of a number of building blocks in quotations. And as we can see, each building block on one side is mapped to a building block on the other side. So in that sense, there is a clear parallelism between the two. And it's also sharper in that the first block only depends on the first pair of integers here, as well as the group G, and similarly for the others. And furthermore, these are glued together in a way using a graded version of the link product that knows about the center of the group G that we're using. And in fact, if you wish, one of the take-home messages of our work, if we're not necessarily particularly interested on this side, is the idea that it is interesting to study essentially easier building blocks and putting them together using this non-trivial product, because this construction actually proves to be extremely flexible and to give many non-trivial MTCs. So in other words, I believe this to be an interesting tool at our disposal in the construction of fusion categories that we can work with. And I think that it's interesting, even if you wish, independently on this part. So there is something interesting in that regard too.
Sorry.
Yes.
It's important that the group is AD.
Well, clearly, if we want to think about a 6D origin, that would be the natural restriction. In this construction, we don't see immediately a reason why it should be ADE, but I would consider that to be an interesting question, essentially to explore more carefully if there is any obvious difference, if it is ADE or if it is not. But from this approach, there is no obvious reason why.
So your procedure works perfectly well with auto group which are not AD.
yes, this sort of map can be considered also beyond the ADA case.
Would it be stupid to ask if there are some class of modular categories where the other direction of arrow would work, starting with a modular category somehow build a manifold?
Well, that would be very interesting. In a sense, we will see that there are, in many examples, there are actually many different geometries that give the same object. That happens sort of all the time empirically. So in that sense, maybe one would have to find a canonical choice. That might be possible. We haven't explored that though. Okay. So this was the introductory part. So in the rest of the talk, I would like to first give a brief review of MTCs and sort of with an emphasis on why their classification problem is at the same time well posed and also extremely challenging. Then I would have to say something about three manifolds and the flat connection part of the problem, because flat connections really are very important for us in order to make sense of this correspondence. It's the guiding principles that we have to define it and to study its properties. And finally, I'll have the chance to actually give you the precise definition of all the various objects that have appeared earlier, and we will see some properties of this map and why we believe it is interesting to study. Okay, good. So let's see. Let me review some aspects of MTC. Presumably, I can be quite brief because many people in the audience are experts in the field. The idea, from a sort of a physics point of view, is that we want to describe the physics of these line operators, the word line of heavy anionic particles, and mathematically, we do this using a category where the objects are the lines themselves, and the morphism are the topological connections between lines. We work in a setting where every line can be expanded onto a sum of a finite number of simple lines, the anions themselves, which obey a non-trivial fusion algebra of this sort, where, as familiar, the fusion coefficients can be regarded as the dimensions of the vector space of topological junctions between the tensor product of AB with C. Clearly, we also have an identity line. Physically, it corresponds to having no particle at all, and mathematically, it provides us the line that behaves as a unit under fusion. So, given this this framework and essentially allowing me to set up the notation, let me also mention other important properties. So here, I'm not aiming at sort of reviewing rigorously the precise definition. I would rather sort of cast a light on the main characters and the main objects of interest from a more physics point of view. So in particular, it is known that among the various properties of an MTC, a very important role is played by the modular data. So the S and the T matrices that graphically we can consider as being associated to this sort of link configuration and to the twisting of the anions. And it was believed at some time, or it was hoped, that knowing the modular data and the fusion data result could be enough to fix the MTC completely. But we know now that that is not the case, as modular isotopes exist, namely MTCs that share the same fusion algebra and modular data, but are nonetheless distinct. So this tells us that, in fact, we have to dig deeper and really look at the actual categorical structure underpinning what is happening here. And in particular, look at the so-called F and R symbols. So the F symbol, as sort of famous picture shows, encodes the associativity of the fusion rule at the level of categorical level. Whereas the purpose of the R symbol is to do the same as far as the sort of braiding operation is concerned. And therefore, it is really the F and R symbols that truly, in a sense, specify the MTC. They are known to satisfy complicated coherence relations and to determine the S and T matrices, provided that those coherence relations are satisfied. So, this is essentially to show that it is a very hard problem, but it's sort of very finite and extremely well posed. And here, I'm just flashing quickly a couple of examples that probably most of you have seen many times. The purpose of these examples is not really to go through them in great detail, but to show that indeed we have access to all this data in a very explicit way. Once we choose, for instance, a basis, a convenient basis to work with. So indeed the modular data in this example take this form. Here I'm writing the spins in terms essentially of numbers mod 1. The fusion rules can be given also in a very explicit way. And I wanted to showcase these two examples because in these examples, it's also easy to write down the FNR symbols in an explicit way to sort of emphasize that really we should be thinking of all this data as what we're really aiming for and what truly specifies the EMC in general. Now, given this structure, a classification problem naturally proposes itself, and also a possible strategy. So one possibility could be to first study the fusion ring and then trying to see whether they can be categorized by finding FNR symbols that are compatible with that fusion structure. Mathematically speaking, this is perfectly well defined. Indeed, thanks to Ocneano rigidity, we know that there are only a finite number of possible fusion structures that can emerge if we fix the rank, the number of anyons. And actually a stronger result was proven later, and namely that not only at the level of fusion, but at the level truly of MTC data itself, there are only a finite number of possibilities once the fusion data is fixed. So we do know that there is a finite list out there, and therefore it is a natural question to see whether we can construct it. And it turns out to be extremely hard. Something that is slightly easier is to focus on the modular data itself. So in other words, it is possible to write down a set of conditions on S and T that are known to be necessary, but not always sufficient. And that's, for instance, the state-of-the-art approach that has given us this remarkable result at rank 11. But to be precise, what is known up to rank 11 is S and T matrix data, whereas it's very hard in this sort of brute force approach to access the FNR symbols that are known to be important in general, and it's something we would like to understand better. So given this, this is the state of the problem that we would like to address. Our work, of course, does not claim to have an answer to these super hard questions, but we hope that this approach can give us potentially new ideas to tackle the problem. And in particular, our idea is essentially to combine simple building blocks to try and build objects that are more and more complex. The advantage of this point of view is that if we focus on the building blocks themselves, in a sense, we know everything about them, not merely the modular data, but the entire categorical data encoded in their FNR symbols. And thanks to this graded product construction, in principle, once this data of the building blocks is known, everything is known of the final product. So not only the modular data, but the entire categorical data. And something that proves important in realizing this idea in practice is the idea actually of sacrificing the modularity at the level of the building blocks. So as we will see, the building blocks themselves are required, are ribbon and fusion, but not necessarily modular. And at the end, what we really care about is the modularity of the final product. So somehow this is the philosophy that we were pursuing. Start with something simple, combine maybe many of these objects using a non-trivial product operation, and then aim at trying to characterize the conditions under which the final product is indeed modular and checks sort of all the boxes.
Is A in the meager center of each of the CI? Is that the idea?
At this stage, A is just a finite abelian group.
Right, but so the meager center of each CI will be also rep of some finite abelian group. And I'm asking if you assume like that there's a homomorphism from A to that group.
I think that might be the case, but we will see explicit examples later, and hopefully the examples will be able to clarify this point. Sure.
So, like in the previous slide where you have like 1 and 2, is there a sense of like a trivial F and R symbol? So like if I have a fusion ring, then like or can I find a fusion ring and there is no FN symbol
No,
consistent?
it's quite non-trivial. Yeah, there's no sort of canonical way given fusion data to just go ahead and construct some FNR symbols. And in general, there's no guarantee that
So it's possible that I have a good fusion ring, but is
in principle that it's possible. So that's what makes this particularly tricky. Yes.
okay. And also in the fusion ring, there is nothing of like MTC, right? It's just like classifying finite rank rings. Is that right? Or
Yes, essentially, yeah. Precisely, yeah, sort of like finding consistent fusion rules, essentially obeying some version of associativity, but
yeah.
indeed, without going at the deeper categorical level. Good, okay. So, right, so let me say a few words about the graded product. This is really one of the main characters of today's talk. To my knowledge, this was first considered by these authors here. And so let's see what is the input and the output of this construction. So we consider a finite abelian group A and well, let's say 2 for definiteness ribbon fusion categories. So those are essentially, from a physics perspective, they're almost MTC. Their S matrix might happen to be degenerate. And we take them to be graded by A so that we can write them in this way. And then once we have this input, the output, the graded product, as you can see, is essentially a diagonal sum of the various pieces combined together. And it sits inside the ungraded product, which would be an analogous expression with sort of 2 independent summation variables. And
Sorry, there's no way that is a construction from 1921. That must be like 2012 or something. From 2021, I mean, this sort of thing is surely goes back to like.
No, well, yes, I mean, that's sort of the where we learn it, but I would be, of course, happy to hear more about the proper history of the stuff. And in sort of like very concretely, if we're given the simple objects of the individual pieces, the simple objects of the outcome, as you can see, are essentially all the combinations that share the same grading. That's the only constraint. And then for instance, the modular data is obtained in a very sort of straightforward way by combining, in essentially the obvious way, the S and T matrices of the given pieces. So it's fairly easy and super and very explicit. And here I'm not writing it down, but in principle, as I emphasized, the full categorical data can be traced through this construction. And indeed, one of the important properties of this notion of product is that modularity is actually a non-trivial question. Like you can give me, for instance, modular input, but the output might not be modular, or the other way around. Maybe the input is not modular, but the output is. So in general, it's a question that has to be addressed, and it's not guaranteed. So given that we want to pursue this idea of trying to construct NTCs, combining building blocks in this fashion, we are in need of an organizing principle, because clearly we have very many options, and we have this issue of trying to find ways to characterize whether the final result is actually modular or not. So given that we need some sort of principle to guide us, we turned to geometry. And so the proposal of this work is to use Seifert 3 manifolds essentially as a way of organizing this sort of construction in 2 ways. It will tell us which kind of blocks we can use. It will tell us which sort of abelian group to glue them together. And finally, it will give us a simple way of characterizing where, in which situations the final product is actually modular. Good. So let's switch gears and let me remind you of some aspects of Seifert 3 manifolds that are going to be relevant for the rest of the talk. One way to think about Seifert 3 manifolds is as circle fibrations over a punctured Riemann surface. And indeed, we can think about realizing them starting from a sort of a trivial product of a genus G Riemann surface with a circle, taking a finite number of points on the Riemann surface, removing small disks around them, and therefore removing entire small solid tori in the 3D geometry. And then essentially gluing back some solid tori, but crucially performing some non-trivial twist, so that essentially which one cycle of the T2 becomes contractible once it's filled in, changes after the construction. So in this way, we move away from a direct product and we access a potentially non-trivial 3D topology. And in fact, one might wonder, are like Seifert manifolds maybe a tiny class of manifolds? Of course, these are not well-defined questions, but something that is actually a well-defined statement, for instance, is that they account for 6 out of 8 geometries in Thurston's program. And as I want to emphasize, and it was also pointed out, all of them are non-hyperbolic, which sort of from a physics perspective goes in the right direction. And here I'm describing the situation of a genus G case, but actually for the rest of this talk and in all our examples, we restrict to G equal to 0. Extension to higher genera, it's an interesting future direction.
I think that's a misleading statement. I think that you should think of hyperbolic 3 manifolds as being full measure, the other ones as being measure 0, and that measure 0 subset is itself divided into 7 different categories. So if you say it's 6 out of 8 Thurston geometries, while that's literally true, I think it's a bit of a misleading statement.
That's fair. Maybe, I guess what I had in the back of my mind, but it's not put out on the slide, is that really we want to stay away from the hyperbolic. So in the non-hyperbolic world, in that sense, we think of them as quite large class. But thank you for the reminder.
So there is a slightly bigger class of manifolds called graph manifolds. I think you get those by gluing things like these over some non-trivial diffeomorphism. So what you will say also generalize to those as they would for a higher genera, or is that also an interesting future direction?
We did think a little bit about it, but we weren't able to sort of make it work in practice. But I completely agree. It seems to be a very
So whatever you would take it and somehow glue it into pieces.
Exactly. But no, at this stage, the sort of like computation, I couldn't start with Seifert management. Good. So among the various aspects that one might want to consider, the thing that we're interested in at the moment for today's talk are flat connections of this sort of for the complexified group GC. And as we already seen in previous talks at this conference, this is a super interesting problem in math, sort of to study character varieties. And it has also appeared in many places in physics in connection to Chern-Simons theory, the 3D correspondence. So there is a lot of interest in the problem of trying to characterize and study the properties of flat connections on this class of geometries. Our motivation here is more modest. And in a sense, what we want to do is to come up with a way of identifying which flat connections will ultimately be corresponding to anyons in our map from a geometry to a fusion category. So we will see that we have to come up with a notion that makes this correspondence work. But to be able to define that notion, we have to look a little closer at how flat connections look like.
Can you maybe give me an intuition why it's important to complexify the group in this context?
That is something that our intuition essentially came from the 3D correspondence. Yes, I think that was our motivation. And the but I see the question, like one might wonder whether a different setting can also work, and we haven't looked at that. And for the rest of the talk, just to be concrete, I will stick to SLN. And as we know, as we have seen yesterday, this amounts to essentially finding group homomorphisms from the fundamental group of our Seifert manifolds to the to SLNC, working up to conjugation. And while there are theorems available in some instances, especially for SL2 and 3 fiber Seifert manifolds, it turns out that actually there are not many theorems available in general. So this seems to be quite sort of, to some extent, there are some open problems in this regard. And we have decided to try a more empirical approach and set up essentially a numerical study to try and see if we can say something beyond SL2 and especially beyond 3 fibers. And in order to make the problem well defined, we have to restrict to suitable classes of flat connection. And what we have done is to restrict to irreducible ones, defined here to be those that have a discrete stabilizer. And since the fundamental group of a Seifert manifold can be written in a sort of very explicit way in terms of generators and relations, now we can literally study matrices that satisfy these conditions. And it's not hard to show that provided there exists an irreducible flat connection, then this central element H is realized by a multiple of the identity matrix, and all the others are actually diagonalizable. So given that they are diagonalizable, we can impose a further restriction. So let's impose that each one of them has all distinct eigenvalues. So this is what we have called an anionic irreducible flat connection, the name being motivated by the fact that these are precisely the ones that ultimately get mapped to the anions of our construction. And something I should maybe mention is that if we consider general big N and little n, we do not expect to have sort of isolated points, but generically we might have moduli spaces of connection of positive dimension. Those are a very super interesting thing to study, but the goal for today is more modest, is essentially to count which connected components exist. Further study is sort of that something we haven't done yet. And this can be done actually in a very explicit way. And here, I don't expect you to follow all the sort of more algebraic detail of this slide, but I wanted to give you an idea of the sort of objects we have. So as I mentioned, this is how the fundamental group looks like. And the goal is just to literally find matrices satisfying these relations. So we can parameterize them if in a diagonal basis in terms of some numbers. We can choose them to sum up to 0 to satisfy the trace condition. And keeping into account some sort of residual gauge transformation due to the Weil action, we can order them in a canonical way for convenience. So as you can see, these conditions in general will cut out a simplex in some flat space. So here is a cartoon of the case of SL3, where we are left with a 2-dimensional angle. And the last piece of information we have to keep in mind is that in order to satisfy this relation up here, that a power of x should be equal to a power of h, the eigenvalues are effectively discretized. So they have to live on a lattice, and therefore at the end, these points that we have in the triangle represent the candidate possible eigenvalues for the flat connection. And in this picture, there is an easy way to characterize which ones are also anionic. They are literally the ones in the interior, whereas the ones where we touch either an edge or a vertex will have repeated eigenvalues and fail to be anionic according to our definition. So this is all, of course, sort of easy. The hard part is if you pick your favorite sort of point in the picture, is there an actual flat connection, irreducible, that satisfies, that exists and has that eigenvalue? And that in general is a hard problem. And we have tackled it numerically to see experimentally what we see. And this is another reason why the notion of an ionic flat connection proves useful, because if you study a generic points that might touch the edge, we observe, so empirically the problem becomes much harder, and we're working on it right now. But if you do restrict to the interior, so the notion of anionic flat connection, then our sort of extensive sort of numerical experiments point towards a very simple conjecture, and namely that indeed all the points are populated. So that ultimately the anionic flat connections will look something like this. This is just, we don't have to go through all the details. This things in brackets is just various copies of these sort of triangles, each for one fiber. And as you can see, we have to glue them all together in sectors. And this is something I should emphasize. So let me go back a little bit to, let's see, here. We know that this H, this particular element in the fundamental group, is central and represented by a multiple of the identity matrix. So it's going to be essentially a root of unity. So it means that flat connections are naturally partitioned into sectors labeled by a sort of a Zn arch. And when we combine all the fibers together, we do find this sort of organization in terms of these. And this is important because maybe it's already something you have already noticed. This is essentially the same sort of structure underlying the graded Deligne product. And indeed, that's how the two sides are sort of analogous. Okay, so in other words, this is a conjecture that we have in terms of this notion of anionic flat connections. And of course, it would be interesting to see whether there is a more analytical understanding and ideally a proof of this. Now, we can finally go to the final part and have a look at the actual map. Now, unfortunately, this gets a little technical in that I will show you some equations. I want it to be fully explicit to demonstrate that this is really completely implementable on a computer. If you wish, it's completely algorithmic and explicit, but sort of the notation does get a little heavy, unfortunately. So let's have a look at the building blocks. So I mentioned that we want to start with something simple and put them together. After sort of many sort of trial, error, and various considerations, we have decided to consider this building blocks here. So here I'm using the notation of sort of these works. This curly C is a ribbon fusion category. It's labeled by SLN, some integer P, and a root of unity big Q, not to be confused with little q, the Seifert data. And ultimately, this is actually defined starting from representations of the quantum group at the same root of unity. But for the sake of time, I will not give you the explicit definition that can be found, for instance, in this papers. What we need to keep in mind for the rest of the talk are just some key properties of this object. In particular, the simples here turn out to be labeled by objects inside the fundamental vial alcove, whose explicit expression is given here, and we will see pictures momentarily. Maybe not too surprisingly, the fusion rules is governed by tensor products of representations. And finally, the modular data, for instance, are not only known, but as you can see, also in a really compact way in terms of Lie algebraic data. Again, I don't expect you to sort of remember these equations. They're not terribly important. It's to show you that
It's the generalization of the vial character formula.
it is indeed, yes. That's right. So as you can see, it's super explicit and also very
The
expected.
relation for the T is the T matrices.
The T matrices are encoded in these thetas. They're essentially the phases, the diagonal entries of T. So it's the same data. Okay, and before showing you the pictures I promised, a couple of remarks. So the first, it's also sort of very natural. This object comes with a natural grading by Zn. And we know it is essentially the anality of the representation of SLN that we want to consider. As I emphasized, this might or might not be modular. And an example that actually we have seen yesterday in one of the talks is this one, this choice of root of unity. in which this building block actually is the same as Chern-Simons at an appropriate level, with this sort of slightly annoying factors of 2 and shifts by the dual Coxeter number. The numerology is precisely the same. And as you can expect, of course, I'm describing the SLN case, but analogous results holds in general. And here are the pictures I promised. So for SL2, we are a rank 1 situation. So this would be vial chamber, but it gets truncated by the sort of the level to a finite vial alcove with a Z2 grading, which is here in this sort of color coding. And then there is the 2D picture for SL3. It's very similar. In general, we would have the entire vial chamber, but it gets truncated into an alcove that has this sort of shape with its own natural Z3 grading. So having introduced these building blocks, I can now give you the explicit definition of the map. Again, unfortunately, this slide is a little technical. I want it to be explicit. I don't expect you to necessarily go through all the equations. But let's see. So indeed, we know that the geometry is sort of defined in terms of data for each singular fiber. The idea is to take each fiber individually, the big N rank of the gauge group, and together there is an explicit formula to extract the root of unity out of this data for each fiber individually. Then we feed it together, we feed it to the building block, and we have with this object. So these are the equations for Q, in case you're wondering how they look like, some sort of algebraic expressions. And the final piece that we have to choose is how to glue them together. We know we are going to use a ZN grading, but there's more than one available in principle. And indeed, we have to make a choice that depends on the Seifert data. And once everything is determined, the building blocks and each own individual grading, we can put them together and get the promised result. But of course, as I said, this is guaranteed to be ribbon, but not to be all. Here is a quick example. Maybe in the interest of time, I'll just highlight the picture if you wish. So these are, I'm thinking of a Seifert manifold with 4 fibers. So this was beyond, was what considered previously in the literature. Each fiber comes with it's sort of its own small vial alcove. This one is slightly larger simply because P is bigger. And then we're instructed to construct products, but respecting the grading. So in principle, we might expect something fairly large, but in the end, we only get 3 objects. And going through the formulae, one can recover all the modular data, for instance, in a very straightforward way, and check that this is indeed listed in those big tables of NTCs. So this is actually something that was known and to exist before. So it confirms that our construction sort of is going in the right direction. But now, indeed, this is very important. I said a couple of times that this is not necessarily modular. Of course, the question is, when is it actually modular? Now, from the looks of it, for instance, if you look at SL2 with 3 fibers, this is the answer. It's a perfectly well-defined answer, but as you can see, it doesn't look particularly transparent or maybe illuminating. What we observe in a large number of examples is that actually there is a simple way of characterizing it. It is precisely the first cohomology group of the Seifert with values in Zn. And this is actually a theorem for SL2 and fibers, and essentially we conjecture it to be true in general. And we have done extensive checks, but really it would be also nice to have a more conceptual understanding.
Sorry,
And yes.
if it is not 0, do you have an understanding of what is mapped into in the braided category?
Oh, I see. So if it sort of quantifies in some sense the deviation from modularity. That's a good question. No, we haven't looked at that. I have to say no.
Maybe might be a related question. I mean, you see H1 of M3 with Zn. It reminds me of the one form Zn symmetry in your initial setup. Is that relevant?
No, it is very relevant, yes. So if we adopt this point of view starting from 6D, this is precisely the condition under which all this, essentially there is no one-form symmetry visible in the UV originating from the choice of polarization of the 60s here. So it's precisely what you're hinting at.
So for instance, could you then instead do like instead of SLN, do PGLN or something to
Yeah, no, that is
to
indeed,
compensate for the one?
so that was the approach that was followed in the regional papers. They were not restricting themselves to this, like allowing a non-zero answer, but then indeed you have to consider PSL connections, and the construction is slightly more. But you're correct. So
Is there a refined version of this conjecture where like the Müller center is actually H1? Like some like
no, right. But I guess that sort of is in the spirit of
maybe you gauge that and then it becomes modular.
Yes, that would be very nice, actually. Yes, no, we haven't explored that possibility, but it would be quite satisfying. Good. And oh, right. And another point that I think is worth emphasizing is the following. In a sense, I have started from some Seifert data and constructed an object. And as we can see, though we do know that sometimes we can change the Seifert data, but the topology remains the same. And so it's very satisfying to see, at least at an experimental level, that if we do change the Seifert data in this way, we do get the same modular data. So it means that sort of this definition seems to actually make sense, and it seems to be that there seems to be some genuine sort of geometry underlying it, and it's just a bunch of integers. And finally, the promised connection that has to do with the anionic flat connections and all of that is that this sort of map that we have constructed is designed in such a way that the simple objects are precisely the anionic flat connection. That's something I mentioned earlier. And another satisfying aspect of this correspondence is that it preserves the Zn gradings on each side. So we know that the lines come with a Zn grading. We know that the anionic flat connections are also partitioned into sectors labeled by an element of Zn. And the correspondence preserves this data. And finally, I'll be brief in the interest of time, we can do something more quantitative. We can say, let's focus on the spin of the anions. So that's some sort of well-defined U1 number. What about the Seifert side? Well, there we can consider the classical Chern-Simons invariant of a flat connection. That's also a phase. And we can verify that indeed they match. So that's essentially what we were able to do using previous results on how to compute these Chern-Simons. We verified that our map is constructed precisely in such a way that we have a match between the topological spin and the Chern-Simons invariant. Okay, so I think these are the main points that I wanted to make. So I think I'll skip the part about the scan. As you can see, there are like pretty tables. If you're interested, you can have a look at the paper. And I'll come to my conclusions. So as I have described for you a prescription, a map that starts from a Seifert manifold and a choice of Lie group and gives you a category. And along the way, we have actually realized that it's important to also study flat connections on this class of Seifert manifolds. We have defined the notion of an ionic connection, and we have some conjectures that are quite broad and I believe might be of interest even sort of beyond the specific problem at hand. A crucial tool was this Deligne graded product that was a long story and was also used by these people. And essentially our results indicate that there seems to be a potentially interesting connection between these two sides that can be exploited as a way to map out NTCs also at fairly high rank. There are many open problems, including, of course, going, well, let's see, beyond anionic in terms of flat connections. We would like to pursue the scans further, how far we can go, how many MTCs we can get. Something that actually we observe also is that we get both unitary and non-unitary models. So in other words, our recipe does not at the moment include a way of select unitary models. I believe that to be important, so we would like to understand that better. I mentioned that in principle we have access to the FNR symbols. So it's important, I guess, both to compute them in examples and to explore whether they have a counterpart on the other side of the story. And as it was already asked, can we go beyond Seifert's? That seems plausible, but we haven't done it yet. And if we are able to do so, then we can explore even more interesting options like surgery, and if this relates in interesting ways. And finally, I do believe remains open and interesting to consider whether there is actually some sort of top-down map from 6 dimensions. That would not, I don't think it's ruled out, but it's not figured out yet either. So it remains to be studied. I'll stop here. Thank you.
More questions?
Yeah, on the last point, you have heuristically an explanation of